All right, so let's get started. Now, before we jump into today's stuff, I do want to show you this quick video. It's 3 minutes, not even.
Good evening. I'm your guest lecturer, Dr. Sheldon Cooper. I was expecting applause. I suppose stunned silence is equally appropriate. I agreed to speak to you this evening because I was told that you were the best and the brightest of this university's doctoral candidates. Of course, that's like saying you're the most important electron in a hydrogen atom. Because you see, there's only one electron in a hydrogen atom. Best and brightest, my sweet Virginia. Let's begin. Show of hands. Who here is familiar with the concept of topological insulators? Don't kid yourselves.
I found another tweet from a student at Sheldon's lecture that Dr. Cooper has taken a relatively boring subject and managed to make it completely insufferable. He looks like a giant insect.
Listen to this one. Does Einstein's theory explain why time flies when you're having fun, but when you're listening to Dr. Cooper, it falls out of the sky dead? Somebody took pictures and uploaded them to the Flickr account.
Wow. How do you get an entire lecture hall to flip you off at the same time?
Apparently, if you're Sheldon, all you need to do is turn your back.
Is your Wi-Fi down? I can't get on.
Oh, Sheldon changed the password. It's now Penny is a freeloader. No spaces.
Thanks. What are you guys doing?
Sheldon gave a lecture at the university tonight. We're reading the reviews.
Oh, how do you do?
Well, picture that Hindenburg meets Chernobyl meets 3 Mile Island meets Strong 2.
That bad, huh?
Read this woman's tweet.
Listening to Dr. Cooper has made me want to start cutting myself again.
Good evening, Leonard, Howard, Raj, freeloader. So, how'd the lecture go? In a word, triumphant.
Really? Triumphant?
Oh, yes, you should have seen those young people. They're thirsty for knowledge, drinking in my wisdom. They've changed a few lives today.
Please let me tell him.
I don't know. I kind of promised Howard.
Tell me what? Actually, we should all share the moment, Raj, if you would. Oh, great. It's about my lecture. That's rather unfair. Downright cruel. Both insects have 6 legs.
So I share that video just to maybe get you to laugh for a moment, but just to remind you to finish filling out your course evaluations if you haven't done so. So if you do that, please try to be constructive in those comments. Like put something in there. Just saying, hey, this class was terrible. That doesn't help me fix anything. So if there was something that you thought, hey, if he did it this way, it would have been beneficial to me, put that in there. Or hey, if you liked something, say that too, so that way I know. But I mean, you can put this class was terrible too. You're allowed to do that, but that's not constructive and helps me. All right. So what we're gonna work on today is the talking about the final exam. So in the thing I have a final exam review, the equation sheet. I think I just left all the equations on there for the whole semester, so you can make that. Remember, you get one sheet front and back, right? So you'll have to be kind of, you might, if you write small, you might be able to get everything on there. But that's there. Also, I did put 2 more worksheets and a concept that had I just put about 50 random questions from previous stuff on there. So if you just want to get practice on some multiple choice stuff again, you can. I mean, you have all your other exams to look at too, so it's there too. But if you just wanted to practice on a computer, I guess you could. All right. Plus, it scores you, and people like to be judged, I guess. All right. So the review, the final exam, is going to have 6 extended response and 25 multiple choice. So we basically, instead of having the 50 minutes, you get an hour and 50 minutes. So you do have, I guess, in one way, you have a little bit more time on the final, right? Because it does have 5 less multiple choice. For the same amount, and you get 10 extra minutes. All right, so yeah, so that's kind of how our final will be. You'll get your calculator, and that'll be that. Now, what I do want to do before we start kind of working through this sheet is mention that if something isn't on this sheet, it will not be on the final. All right, so if you're like, hey, but what about this? Is that going to be on the final? And then I'll be like, well, is it on the sheet? But then you're like, but I didn't. And then it's just going to be this, well, yeah, if it's not there, it's not on the final, right? That's why we made this sheet, is so you know what's going to. It doesn't guarantee like you'll know the question, but that it will show up somewhere in the final, right? Now, what I want to do before breaking into this is I want to talk about, take a step back and look at the semester. So the semester is broken down into chunks and segments. You may not have recognized it because your semester is chaotic and you're doing like 6 of these types of things all at once usually, but this is what we really did. So the first thing we talked about was motion, right? If you think back, the first kind of exam roughly covers motion. We talked about 1D motion under different conditions, with and without acceleration. We talked about, if you look, we talked about throwing and dropping objects, which we called free fall motion. We talked about projectiles and things moving in 2 dimensions. So we did motion. Then after motion, we talked about Newton's laws, right? Now, Newton's laws, we had 3 of them, or second and third law. So does anyone remember the first law? No, my mind. Or no, you have, yeah, you're fine. All right. What was the first law? So you remember my pizza? My pizza. You remember my pizza?
It's inertia.
It's inertia, right? Because remember when I was driving in the car and then I suddenly had to hit the brakes, me and the car stopped and my pizza continued moving forward because that's what pizzas want to do in the absence of forces, right? So the first law is the law of inertia. It tells us what happens when the object is at rest or if it's moving at a constant velocity. Then what's the second law? F equals ma. We call it the law of acceleration. It tells us what happens when forces are applied to an object. When my pizza hits the front dash and then falls to the ground, we found out what happened to it because forces were applied. And what's the third law? The law of
Equal and opposite.
Yeah, we said that we call it the law of interaction, right? Or a lot of times people learn it as the law of action-reaction, right? And the way we said it is that you can't touch something without it touching you, correct? And so the idea is that forces between 2 objects are equal and opposite. And that's probably of the 3 laws, that's one that bothers people most. Like when you ask test questions about it, people just refuse to say, oh yeah, they're equal and opposite. But the idea is that that's how it is. And this actually, the third law is the one that leads us over to collisions and momentum conservation, right? That's how we derived it, was by looking at the force between 2 objects and saying, oh, these are equal and opposite. And so just remember that. Now I'm going to give spoilers. This is a spoiler for you. Ready? These will be on the exam. All right? Spoiler alert. Newton's laws are on the exam, just so you know. They're here. But those, you will have questions about the 3 laws. It's physics. All right. So the next thing we did is we talked about that. We talked about the second law in rotation. Right? And this was all related to torques. Things spinning about internal axis, things of that nature, balancing torques, right? Oh, we're going to hang 2 masses from a thing with a pivot, anything like that, torques. Torques are forces that cause rotation. So we had a whole thing on that. Then after that, I had to lump two things together just to fit them in because we only have 4 exams and not 5. But then we introduced momentum because it's one of our 2 big conserved quantities. And what was the other one? What's our other conserved big quantity? We just took a test over it. My goodness. Energy, right? Energy is our other conserved quantity. And then we finish out talking about fluids. Well, fluids were kind of dispersed through the last like 4 weeks. But we then have these 6 major categories, right? Does that make sense? Do you know why I mentioned these 6 categories? Huh? They're on the test, but I want you to think about 2 numbers I gave you just a minute ago. And then you'll make the connection, I hope. How many categories for final exam questions are there? How many extended response questions are there? There you go. I'm not telling you what they are, I'm just telling you these will probably be what those overarching concepts will be from, right? I can't tell you what the questions are, but these are the 6 main categories of what we looked at this semester. All right, so let's dig back into then this stuff. All right. So what you can think about is we have motion, and now we can start digging into these concepts, right? There is a lot under each one of these concepts, and that's what makes the final a little bit trickier because there's a lot of little pieces. I can move this up. So the idea now is we want to talk about motion. Let me throw this sig figs unit conversion. You should know how to multiply 2 numbers with different significant figures and divide them and add and subtract them and come up with the right number of significant digits. And you should also know how to convert units. Unit conversion is important and sig figs are important. We test them about them and we talk about them all the time. I personally don't grade you harshly on them, but know this. If you're going into science or medical field, having these 2 properties is very important. One is if you're going into a medical field, you misdo a unit conversion or you misread a unit or something, you can cause harm to somebody, right? That can be very dangerous. On the science side, just as a personal example, when I made a publication, I submitted it. I had all my data tables and everything set up correctly as you should. And then somewhere in there, when I referenced the number, my brain just wasn't thinking. My table had 3 digits after the decimal, and I typed in, oh, this value of 2.34. I didn't put the 3rd digit. And I did that a couple places. And the editor just reamed me and said, hey, this is unacceptable. In science, we report the correct number of he was literally what, are you a doofus? Are you something wrong with you? It's a big deal because you're in science, right? You're supposed to hold yourself to a certain standard. So even though we don't it's important to know these things and do things well, right? Especially if this is what you want to go do as a living, right? So it's important. So that's there. That will show up somewhere through the final, right? All right. Next up, relationships. So we have these equations. We said that distance is velocity in time. Right? We said the distance is velocity times time. We also have these other equations that I'm just going to write up now. So we have them. And we had v final squared is v initial squared plus 2a delta x. And then we had v final equals v initial plus at. So this equation was a specialized version of this one. We said this equation is only because we have no acceleration, right, at that moment. Now, there are other things you can talk about where you can get to this and you can say, oh, well, inside of some really small time interval, I can look at this part and that's the slope, and you can do all these other things, but in general, this is our no acceleration equation, and then you can have your position change with acceleration as well. So we have these four main equations that help us describe motion, and we can use these in 1 and 2 dimensions. Now, one of the first things we did to even make our equations is we looked at graphing. We looked at plotting positions and times, right? And there was 2 kinds of general conclusions we took out of this. The first one is you could have something that looked like that, and we said, oh, the slope of that line represents velocity, right? So the slope of position versus time, this gives you velocity. And the next part that came out of that is we said, if you have this slope here and then you plot this in velocity versus time and you go this way, you get some kind of flat line because this is a constant v. Right? So a sloped line here is constant velocity there. And then we could do the third graph, and if you have constant velocity, that tells you that your acceleration is 0. Right? Now the other thing that we could take out of here is you can get a curve. And curves in position versus time tell us what? Acceleration. This tells you that you have an acceleration. Now there's 4 curves. You can think of the smile and the frown, right? So the smile is curves this way and the frown is curves that way, and they all tell you that the system is accelerating. The smile and the frown. Now if you have a curve here, that tells you in this place you have a slope. So curvature here, this gives you slope over here. Does everyone follow that? So if you have some kind of curvature here, you get a slope over here. That's terrible. Now, what does the slope over here represent?
Acceleration.
This is acceleration. Okay? So we know that line, constant v, curve, that gives us a slope over here. That slope tells us there's an acceleration. All right. Now, the other thing that we took off this, I have to draw another one of these in a second, but the other thing that we talked about was what does an area underneath the VT graph mean? It's distance, right? It's the displacement. Because if you take velocity times time, that gives you the displacement. Because velocity times time gives you that area. Right? Matter of fact, that's how we derived this equation. We derived this by looking at just the area underneath our curve in velocity time. Is everyone good with that? All right. Now I do need to, I'm going to switch these two real quick. Just because I need to draw moving graphs momentarily. And then the other thing that we mentioned when we're looking at our equations is because these are all vectors, and I did not draw any of my vector symbols, but they are all vectors. Velocities and displacements and accelerations are all vectors. And what that tells us is they can interact and they give us different results. So what we want to think about is if we're looking at this equation here, and now we have a velocity versus time graph. The first result we can think about is this. This is a certain result because this tells us our velocity initial is positive, and what is the acceleration? The acceleration is positive. We call this speeding up. This means you speed up. Now the other way, because these two signs match, so that's a speed up. Now over here, this is also going to be the same thing because VI is negative, and the slope of this is also negative. So both of these are speeding up, right? Because the signs are the same. And when we look at this, if you have negative, negative, that makes a bigger negative number. the value is getting larger with time. It doesn't matter that it's getting more negative, it's still getting bigger. And the same is true on this one. Now our next graph over here, VT, we also have two other cases to look at. The first one is this, right? We start with some V initial positive, and the acceleration in this case is negative. And this is what we call slowing down. Notice that a slowdown is when the signs are opposite. But it can't, this isn't the only one. You can also do this. This one you have V initial is negative, but A is positive. And that's also slowing down because your value for the final velocity is getting smaller. So we also said that anytime your lines tend towards the time axis, that means you're trending towards zero. These are slowing down. Right? Is everyone good with that? Does that sound familiar? And then the last thing we said you could do is if you cross the time axis, we said that this means you are changing directions, right? And those are almost all the different things that we said you could do with position, time, and graphs and all those velocity and times and things like that. All right? So those were all the different things we looked at in terms of graphing. Is everyone okay with that? Then what we'll do momentarily, we'll quickly go over the different motions real quick. So the one thing we did with those three equations, we solved systems that could accelerate, right? We looked at, a car speeding up, slowing down, things, animals running, the gazelle stopping and the deer running in front of the car. I don't know, all those different problems we had with accelerations, right? One of the ones that was kind of different though, was when we talked about projectiles. We had two different not projectiles, we talked about throwing things straight up and down. So when we talked about free fall, we said that if you launch something in the air with some initial velocity, it goes up, it reaches a y max, and we said at y max, Vy is 0 at the top, and then it comes back down. Right? And anytime the object starts and stops at the same place, we said that time up equals time down. And then your total time, t total, was just equal to 2t up or 2t down, whichever one you could find. Right? And this was because of symmetry. We had symmetry. And the other thing that comes out is that our ay is g and it's downwards. Right? ai, your acceleration, ay I meant. ay is g, it's 9.8, and it's pointed downwards. Sound familiar? Now, the next case we had is you could be up some distance above the ground, right? Where you have some y initial above the ground, y final or y ground is down here. And you can throw something straight up with some initial velocity. It'll go up, it'll reach a y max with Vy at the top, or Vy equals 0, and then it comes back down. But here we have to pay attention that T up and T down are different. They are not symmetric, right? Because you're going to go up a certain distance, but you're going to fall further. And here, T total, you have to add up differently your time up and your time down. But your AY is still G. And so I always recommended find T up. T down is just a free fall problem. And then you add them up and get T total and you can find the velocity or whatever else you need to find. Is everyone good with that? All right, then I'm going to step over the vector part for a moment. And I'm just going to talk about the projectile case because that fits in nicely with this. And so when we have projectiles, we have a similar setup. So here, though, we launch something at some VI. And what happens is the object does something like that, right? You launch something at some VI, which I exaggerated that initial line, but the idea is that you have some VIX and some VIY. And in our projectile, we said again, it's Vy top equals 0 at Y max. Right? We have that same condition as we did before. At Y max, Vy top is 0. Now, because we have to break things into vectors, we remember that Vix is Vi cosine theta, Viy is Vi sine theta. We remember that we have to break things into components. You can't use Vi for Vix and Vi for Viy. That is wrong. Vectors have to be separated out. The other thing we said when something is launched in the air is that Ax was 0 and Ay is G and it's directed downwards. So really, projectile motion is the stitching of two solutions together. In the Y, your object goes up and comes down, and in the X, it moves along at constant velocity. And when you stitch it together, you see your object doing that. So this is basically our projectile. Now here, we notice because of symmetry again, this is time up equals time down. And then you can just double the time to get the total time that you're in the air. Now we do have one other projectile case that you could do. You could stand on the ledge of something and throw something up into the air. Now when you do this again, here at V top, V top is equal to 0, Vy, and Y max sits at that same thing. So it's basically you have this, except you threw it out. So you launch with some initial velocity, Vi, and when we draw that vector, we see Vi, here's Vxi, and Vyi at some angle theta. And we separate these into the components, and we get the same problem again, where you have T up here, T down over here, and again, T total is T up plus T down. Right? And so you can then find all the different pieces along the way that you need, right? So you can find your Y max, and you know that this is your Y initial, this is Y at the ground, and you can solve for the different pieces and stitch the puzzle together. Now, the one thing to note is the following. Because of this angle, you always have to break things into components because vectors are, you have to apply vector math, which is component math. But notice that this problem here is this when theta is 90, right? It's a specialized case of this. Our other specialized case was when the angle was what? Remembering back to the beginning of September when there was still warm air and flowers and the sun. So 90 is a good angle, and what's the other angle we usually gravitate towards? 45. No, that's a special angle too. But the other one is the horizontal launch. When theta equals 0, we said that this is our horizontal launch. Right? And when we talked about the Gatorade bucket the other day, we said, oh, the fluid it launches out horizontally, and then it's just under free fall, and it travels some distance in the X and then hits the ground, right? So that was our other, and we also used that to prove satellite orbits as well, when we launched things horizontally. So that's a specialized case, the horizontal launch. Those are our two specialized cases. 45 is another special case that gives you maximum, without air resistance, that gives you maximum travel distance. If you're throwing on the ground. So these are all of our different special things for projectile motion and for dropping and throwing objects, right? Now, the only other thing we need to mention out of motion is to talk about vectors. So we said a vector, if this is some vector A, and it's at some angle theta, it can be broken into components AY and AX, such that AX is A cosine theta, AY is A sine theta. Then we also, using other fun math, we said that AX squared plus AY squared square rooted gives you A, right? And that our angle theta can be defined with the tangent of AY over AX. Right? And so what they're mentioning here is you should be able, if given A and then theta, you should be able to find AY, AX. Given AX and AY, you should be able to find A. Given AY and AX, you should be able to find the angle. You should be able to, given some of these pieces, you should be able to do any type of vector math that we throw that you're asked. Is everyone good with that? Now, the other part that comes out of this is if we're going to add two vectors, you have some vector A, here's at theta, and let's say you add a B, a vector B, at some angle, we'll call this alpha, just to keep them different. Now, when we want to add these two vectors, please clean up well, we know that this is vector R. It's the addition of A and B, but we cannot add A and B directly. What we really need to do is we need to have AX here and BX here. So there's BX, AX. And then we have some AY here. Let me redraw BX. There's BX. And here's BY. And what we see just graphically, we see that by adding these two up, Rx, which is part of a new triangle, is AX plus BX. And then this part of the triangle, RY, is AY plus BY. And that forms our new right triangle R, which is the result of adding A and B together. And so here we can say AX is A cosine theta, BX is B cosine alpha, so that Rx is AX plus BX. AY is A sine of theta, BY is B sine of alpha, such that RY is AY plus BY. Okay? So you should be able to take components, add vectors together using the component method, which is really what we do in chapter 5 with the second law, right? That's how we kind of solve the second law. Now, the other thing to remember then is R is the square root of Rx squared plus Ry squared, and then theta would be the inverse tangent of Ry over Rx, right? And the reason we teach that we practice this back here in 3 is, one, it's useful for projectile motion and two-dimensional motion, but it's also the backbone of chapter 5 when we want to add vectors. Because all the forces are vectors, and you break them into components and use the components with components. Okay, X's go with X's, Y's go with Y's. Is everyone good with that idea? All right. Then what we'll do, look, a few more minutes. Yeah, going faster. All right. Let's go now. Now we're going to move into chapter, that was like our first couple chapters. Then chapter 4 introduces our force catalog. So the force catalog is kind of the list of forces that can be used, right? Now the first one in our list here that I have, yeah, we already talked about the first 3 ones, so we're good there. But the force of tension. So if we think about tension, it's like when we attach some kind of rope, chain, cable, string, cord, I don't know, any type of thing like that, and then you pull on that. And the thing to remember is tension forces act on that line. They cause that force to occur on that line. And this immediately tells us that we need to break that into some kind of component, right? So we have to break this into like a Tx and a Ty. Because that force is acting at an angle, which means it's got components, which means we have to do components over there. So this is a tension. It acts on a line from a string, cable, chain, rope, cord, something that you can pull and make taut. That's tension. The next one up there is going to be weight. And weight acts in what direction on all objects? It acts straight down. And weight is defined as mg. Don't let that fool you, because a lot of times we'll say, we'll give you the mass and not the weight, and people just want to use the mass and they forget about gravity. Okay? Weight is a force, mass is a property of an object, right? It's the collection of the atoms. So weight is a vector that pulls straight down. It doesn't matter what reference frame we're using, right? Even if we're on the incline, weight works straight down. Right? It always works straight down. So the next up is the spring force. And the spring force, if you remember, the spring force is what we call the restoring force, right? The spring force, if this is our spring at its natural length x0, we said that if you compress, so you push this way, we said the spring force will act the other way, and this is some x final. So this is that delta x. Or we said that if you pull on the spring this way, you apply some force, then the spring force works against it. The spring force is a restoring force that always works opposite the direction the force applied to it. Now to calculate the spring force, we said it was K delta, the absolute value of K delta x. So you take, for the delta x, it's x final minus x initial, which is the natural length of the spring. And so the spring force changes as we stretch it farther or compress it more, it grows in strength. And we said that this K is the spring constant. Right? And that was our spring force. It's also called Hooke's law. Is everyone good with that? It's a restoring force. Next up is we have the normal force, and the normal force acts out. Perpendicular from surface to object. So in this case, the normal force would be this way, and over here, the normal force is there, because it's always acting perpendicular from surface to object. Now, how do you determine the normal force? You can only find this guy by summing forces. And notice, because the normal force isn't just the weight. Now, if this tension force isn't here, yes, the normal force is the weight, but over here, the normal force isn't W, because remember, when we have W, we have to break this into components, right? We always have to have a WY here, and a WX there, and in this case, WY is the normal, not W. So the normal force is found by summing forces. And since we're here, I'll rotate this now. And remember, whenever we're on an incline, we rotate our reference frame. And in doing so, what we say is that WX is W sine of theta, and WY is W cosine theta. So that notice that the normal force is found by summing the forces, not just the weight. It's not just the weight, unless you're on a level surface and nothing else is acting on it. Even here, notice the normal plus the tension and the y equals the weight. So the normal force is reduced because this Ty helps contribute to that. The normal force only works as hard as it has to, right? It's gonna, if it doesn't have to support the whole weight, it'll let Ty support some of it, right? It'll share the burden. So the normal force is found by summing forces. The next one up is the apparent weight, and we said the apparent weight was what? It's okay. The apparent weight we said was the normal force because it's how you experience your weight. So the normal force is also related to the apparent weight. It is how the object experiences its weight. And then the whole thing related to this was the elevator, right? When we were in the elevator, you're standing on the scale, your apparent weight changes if the elevator accelerates up and down, right? And so the normal force is your apparent weight because it's how you experience your weight. Also, if you look at number 5 there at the bottom, forces and accelerations in circular motions. We said this is how roller coasters and amusement park rides work because that normal force changes as you go over curves and through dips and upside down. You feel different. You feel your weight differently, and that's what people pay big money for, right? You can just jump around, I guess. This is the idea. The normal force and the apparent weight are one and the same. They're how you feel about your weight. Next up, we said was static and kinetic friction, and we said that there's 2 kinds. So the first type of friction is static, and static friction arises because the velocity is 0. This is for static, it's not moving. And friction is a force that does what? So this is when velocity is 0. So friction in general works which way? That's what I should have asked. It works parallel. It's a force parallel between surface and object. And yes, everyone was trying to get to me, yeah, it opposes motion and works against motion. That's true. But remember, it's always parallel. So the friction force, if you apply a force this way, friction will be parallel between surface and object. Now, the other thing we said about static friction is it works up to some maximum value, right? So static friction will match your push up to some maximum value, and then once you break it, you move over into the other kind. But we said that static friction was mu static times the normal, where mu static is a property of the materials in contact, and the normal force is how hard they're interacting together, right? So this was the force of static friction. Now the other one we had is if V is not 0, and then your object is moving, let's say this way, you have the force of kinetic friction. So kinetic friction opposes the velocity vector. And it too is a property of materials in contact, mu k times the normal, where mu k is a property of the 2 surfaces, the 2 materials in contact, and the normal force is how hard they're being pushed into each other. Typically, in general, mu s is bigger than mu k for most materials. Yes, there are some materials where they're the same, and there are some, I'm sure some material scientists could engineer one that has a higher static value, a higher kinetic value than static. I'm sure someone could do that under weird conditions. But typically, in most materials, US is bigger than UK. Okay? So this is our force of friction. It's parallel between surface and object. So our takeaway right now is if we're in contact with the surface, there's 2 things we should be worried about. Normal force, friction force. Because those are the 2 things that arise in contact with the surface. Is everyone good with that? And so the idea now, oh, we're missing one. Universal gravity. So universal gravity, this is just an attractive force between any 2 masses, right? We talked about this because it's an important law in nature. All matter attracts other matter. We have yet to find any matter that repulses other matter, right? You do it, you probably have a Nobel Prize within 5 years of that discovery, just so you know. Even antimatter attracts other, it's still an attractive thing, it just has a different charge. It annihilates upon contact. But the idea is all matter attracts other matter. That's why we have the galaxies and universe and all that stuff is always attractive. Matter attracts other matter, stars, planets, all that works because of this. This is also going to be the basis back part of when we talked about orbits and orbital mechanic things. This helps dictate that, like orbital speeds, orbital periods, things of that nature. So these are our laws. Now these are our forces. Now what we're going to do is eventually we're going to then say, notice the next thing is drawing force diagram. So knowing how these forces work will allow you to draw force diagrams. Second spoiler of the day, you'll be drawing force diagrams on your final, okay? At least one, if not more. So force diagrams are another important thing. You should be able to draw a force diagram. It helps you process that information. The other thing then is to apply the second law. Now we said that the second law was the law of acceleration. And so the idea is, the general form we said was this. We will break it, of course, into two parts because we will break our forces into vectors and some x's with x's and y's with y's. So the general thought is you draw a nice picture, label it correctly, then you know what forces to put into your sums for the x's and y's. We can then know that, hey, if an object moves at a uniform speed or constant speed, those are our buzzwords that the acceleration is 0. That helps us find it. The object is at rest. Acceleration is 0. Like we use our motion buzzwords to then apply that to the acceleration to know what's happening with our acceleration. The other part that comes in is you could be on an inclined plane, remembering to rotate your axes. You can, I'm going to pull this down. It's not going to rotate, but you could be on an inclined plane. You could also be pulling a box at like an angle, which is important to do then, because you have to remember to keep breaking your forces into components and solving them independently, right? That's the whole idea. So then you'll be expected to do that with your second law. Now, I guess, yeah, when we come back on Friday, the idea will be, we will briefly mention this, is for when we went through circles, right? This was not torques and that type of circular motion. This was something going around a curve, over a hill, through a dip, or upside down on a roller coaster. That's what this one is for. That is not for the one spinning about an internal axis, right? Those were two different types of motion. So this one was the one that also led us to like our orbital periods, orbital velocity type things as well. But you should be able to use that as well. You should be able to sum forces from either going in a car around it, like a car takes a turn, going over a hill on a roller coaster, going through the dip on the roller coaster, going upside down. Those were the 4 problems we had there. We sum towards the center of the circle. And we'll remember that towards the center is positive, away is negative, right? You always remember. Towards the center is positive, away is negative. When we put our forces. All right, that's all I have time for. I will look at you tomorrow. Friday. Thanks.